I really should have some music over it or something. Maybe I'll look into that. So this lecture is about why does the Middle East and the world generally look quite like that? And this is due to the nature of the Earth and of plate tectonics. This is from the fact that the Earth's crust, the lithosphere, is just a crust that is over a somewhat molten mantle and asthenosphere. And the mantle, because it is fluid, moves around, and that moves the crust, the lithosphere, in what is known as plate tectonics. We start getting suggested of this sort of thing by a man called Alfred Wegener at the beginning of the 20th century, who proposed the theory of continental drift. Now, the idea that the continents sort of fit together like some massive jigsaw actually went back centuries, but it was Alfred Wegener that first proposed the idea as a theory, but he didn't have a mechanism, and so a lot of people didn't think much of it. It wasn't actually until the 60s that people like Canadian geologist J. Tuzo Wilson, U of T professor, who developed the overall theory of plate tectonics. So this involves these plates which make up the Earth's surface, and you'll have boundaries like mid-ocean ridges, and you'll have boundaries like ocean trenches. And so these are what define the boundaries of the plates. Now, the plates relevant to the Middle East include the African plate, the Eurasian plate, the Arabian plate, and the Indian plate. So the way this works is that upwelling of mantle separates the crust, which then goes off in different directions and eventually will go down into the trenches and be melted and reused again, sort of like recycling. Here in this section through, we can see the divergent boundary is where the oceanic crust separates and goes its different ways. It also can separate continental crust, and this will create rift zones at first, and eventually can create a narrow ocean, and in fact a great ocean as big as the Atlantic, which was originally wasn't there at all. Here the series of drawings show the upwarping from a hot spot underneath, then it becomes a rift valley, then becomes a linear sea, and then starts to develop a mid-ocean ridge. This is actually what the Red Sea looks like now, with a mid-ocean ridge which has developed an oceanic crust which is developed at the bottom of it. Here is the Red Sea, and you can see the network of rift zones which have developed in this part of the world related to these upwellings of lava. And wherever you have this upwelling, it'll break the Earth's crust into three directions. This is the kind of volcanism associated with these parts of the world. It's called a shield volcano because it looks a bit like a shield. And these are made of basic or basaltic volcanism, which is very fluid and travels across the Earth's surface quite rapidly. Here, at the north end of the Red Sea, you can see this upwelling created fault zones going up into the Gulf of Suez, the Gulf of Aqaba, and the Dead Sea. Volcanism here in Syria is also of this basaltic nature, making shield volcanoes. Here you can see a shield volcano I photographed outside as I was flying on the way into Damascus one year. Here is a satellite. I wasn't actually in the satellite at the time. It was a satellite image of with thermal radiation that shows you how hot the ground is. And what this will show you is that this very red hot bit here is where the most recent volcanism was, which had not been covered with vegetation. So you can see here previous flows of lava going across the landscape. So another type of boundary is called a transform boundary, where you have two plates going past each other. Now this actually happens in Syria, where one side of Syria is going north, the other side of Syria is going south. Now this is what happens at the monastery where I worked in Syria, Dir Marmuza. And if you look at where this red line appears now, it's going to go away again now, you can see there's this crack that goes down. And this is a part of this massive faulting system. And an earthquake did a great deal of damage to the monastery. Here, this picture taken in the early morning of the north side shows cracks which are from the building being warped in this direction. This in turn led to parts of the walls just falling down and being replaced. This is an interior shot, and it shows you this is actually the chapel, the church, with frescoes of saints and things on the side. And here you can see these large, well-cut blocks are the original construction, and these round blocks with wood are from the earthquake damage repairs. So the frescoes that you saw previously actually have dates on them, and so we can see exactly when the earthquake was. And there's a series of earthquakes that occurred in Western Syria at about this time. In 1114, there was, that's Dir Marmuza right there, of course, an earthquake in actually southern Turkey. Then there was the Great Aleppo earthquake of 1138, the Great Hama earthquake of 1157, and then this earthquake, which is quite near Dir Marmuza, is actually probably the one that damaged the monastery. And then there was another one in about 1202. So the other type of boundary in plate tectonics is the convergent boundary, where the plates come together, also known as a subduction zone or destructive margin. And so here you can see the plate going underneath the other plate. This one is going underneath continental crust, and this one is going underneath more oceanic crust. So here you can see it's being destroyed. It's the destructive margin, which is different from the constructive margin or divergent boundary. And it's also called a subduction zone because it's subducting underneath the other one. We have a major one of these in the Middle East, known as the Zagros Thrust, and also the Oman Thrust and the Troodos Mountains, which are basically part of the same system, from when Eurasia, I should say, and Arabia, the Afro-Arabian plate, slammed into each other, and the Arabian plate is now being thrust underneath Eurasia. This is very important in the distribution of stuff because it's quite as closely associated with copper reserves and other materials which you'll become aware of. But copper was a very important material from Oman, and also was so important from Cyprus that it's why the island is in fact called Cyprus. So at these convergent boundaries, you will have oceanic crust meeting oceanic crust. And so you have these wide open basins where you have limestones forming. So these animals will die to make stone. And these are the organisms that have died to create that sort of rock. You will have oceans being near continents like this. And here you will get detrital rocks, like sandstones, which are made of sand-sized particles, and shale, which are made of clay-sized particles and things like that, and conglomerate, which are made of cobbles and pebbles and things. One of these is, of course, the Nile Delta, which is a whole lot of detritus, mostly actually from Ethiopia. Here is the Shatt al-Arab, which is where the Tigris and Euphrates flow to. And here you can see sediment from the Taurus and Zagros mountains. So, this is associated with volcanism. This is a stratovolcano. There's one here, and there's one here. So here you can see where it's creating an island arc of these volcanoes, and here you can see along a mountain chain you have the same sort of volcanism. These stratovolcanoes, they're tall and pointy, not flat like the shield volcano. So these tend to have a lot more silica in it, and so they're called acidic igneous rocks. And you'll have volcanoes made of rhyolite. And of course, this is the original the other Vulcan, who lived underneath a volcano like this in Etna, in Italy. And you will have plutons, granitic plutons. Plutons are named after Pluto, of course, the god of the underworld. And so because they are developed under the world, and they cool and become very crystalline because they're underground, whereas the same chemistry of igneous rock will come to the surface and become rhyolite. So they're exactly the same chemistry, but because one has come to the surface, it will be very fine-grained, and one has stayed below the surface, it's very coarse. So this is the sort of thing where you get near subduction zones or destructive margins. Mount St. Helens is a very well-known stratovolcano, and did what stratovolcanoes tend to do, which is blow up. If you think of other volcanoes which blow up, like the one near Pompeii, this is exactly the same sort of thing. A stratovolcano, tall and pointy, blew up, and it used to be called Soma and is now called Vesuvius. This is actually much smaller, as you can see, than the original mountain. Now, this blew up in 79 AD and created a bit of a disaster at the time, although it made very good archaeology, of course. And you had this ash fall going down south, covering Pompeii, and massive pyroclastic flows going down towards Herculaneum, Pompeii, Herculaneum. Now, there were like these big things falling out of the sky, called bombs for some reason, but most of the things that killed people were gas and ashes, and so they were all asphyxiated and smothered. This is at Pompeii, though. At Herculaneum, which is closer to the volcano itself, when the volcano blew up, oh, that's a piece of bread, by the way, it came down to Herculaneum and was this massive, very fast, red-hot cloud. And when it hit the people on the beach at Herculaneum, this man was standing on the beach, waiting, hopefully, for boats to come to take them away from the disaster, and he was dead before his body hit the beach. But, it was very bad for him, although he died very quickly. But it actually gives us one of the very few examples of a Roman soldier that died with his equipment on. So it's actually quite useful. And this is what he would have looked like. He didn't wear armor, of course. He was just on the beach. Çatalhöyük is actually quite interesting. Çatalhöyük is a very important Neolithic city in southern Turkey, and is also relevant to this type of geology. They had an extensive weirdness going on with bulls and queenly ladies with cats. And what was important there was obsidian. Obsidian is volcanic glass of the same chemistry as rhyolite and granite, but it's glassy because, it cools very, very rapidly. And so this very desirable volcanic glass, which is very good for making tools and weapons out of, was traded widely around the Middle East. This red distribution on the left is actually from the volcano, which is right next to Çatalhöyük. And this wall painting at Çatalhöyük, this is a copy of it, you see, actually has a volcano erupting, and it has ash fall. It's showing you ash fall. So it's a very typical stratovolcano doing its thing, depositing a bit of flow of obsidian, which you can then turn into things, and ashfall, which will probably be very unpleasant if you get in the way. See, here's the volcano in the original thing here, you see. Granite is also very useful, of course. It's a very nice building stone. Aswan Granite is very famous. It's from Aswan in Egypt, and we'll be talking more about that another time. Here, for instance, is the same granite in Syria. The Romans used to take it everywhere. They liked it a lot. So, you also get continents colliding with continents. Now, when this happens, you get really, really big mountains. And probably the really, really big mountain you're thinking of is exactly the one we're talking about. The Himalaya-Hindu Kush Orogen, which is the birth of mountains, is from two continents, the Indian landmass and the Eurasian landmass, slamming into each other and creating significantly sized mountains. It also moved very, very fast, much faster than other plates seem to move around. So deep below these mountains, you will often get metamorphism. And we will be talking more about metamorphism later on. And metamorphism is due to a couple of things: temperature and pressure. And so the more it's cooked, you can see here's the temperature, the more it goes along this way, and the more pressure, the more it goes this way. So quite often it's a combination of both. When you go, the more further down you go below some of these very deep mountains, because they're as deep as they are as high, you see, it'll be getting hotter and more pressure. Whereas other places where, say, you have a granitic batholith or pluton intruding the country rock, you'll just get a lot of temperature, so it'll be along here. So metamorphism is very interesting and varied. A very important metamorphic rock is actually marble, which is what limestone used to be. Remember limestone in those shallow seas made of organisms? Gets metamorphosed and turns into this very popular stone for carving people out of. So this very amusing GIF shows you the Earth doing its thing, and you can see at one stage it was all together. See, I was saying how the Atlantic used to actually just be a rift, and it got bigger and bigger. There you go. So here's India. See India, and wham, straight up there. Doesn't mess around. Here's Africa and Arabia still attached. As it gets further away, it starts to separate. And it slams into Eurasia up here. Now, you can see, like, here's Greece. And it's probably trying to make you think Greece is just like this island floating around. Greece actually would, in fact, have been the surface of the sea at this time. All of these things along here are actually bits of sea, and which have been rocked up and metamorphosed, which is why it's got a lot of limestone in it, which has been metamorphosed into marble, because it used to be seabed and then become mountains. So here we have, so here's the Zagros thrust, making the Zagros Mountains and Taurus Mountains here. Here is Africa, the African plate. And here's the Arabian plate and Eurasia, and the Indian plate's over here. You can see it's really rocked up, the mountains here. This is the Hindu Kush. And so this is why this looks the way it does, because of all these plates slamming into each other. You can see Anatolia and Iran are bits of other land masses which have, shall we say, accreted on the edge of Eurasia as it was going across, and the subduction zone used to be in front of it. Some massive trench which then got filled up with Arabia. And all that's left of that sea is the Gulf, Persian or Arabian, depending on your point of view. And this is opening up. And The upwelling has created this highland which shows you the ancient Precambrian basement, rather like the Canadian Shield in northern Ontario. So that's how it got to be the way it is. So next time I'll show you why there are green bits and not green bits.